Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
So we've talked about estimation of random variables, and in particular we've talked about not so much a precise theorem, but just a general procedure for finding interval estimates, confidence intervals for an unknown parameter. And the general rule was you try to find a pivotal quantity and manipulate that into a known distribution, and then use quantiles of the known distribution to get a band. So we're going to really start chapter 9, which is some more detailed properties about point estimators, because we defined a couple of basic properties of point estimators. So just to remind you, the expected value of, I'll say, just a common notation is theta hat for theta. So if you're estimating an unknown parameter theta, then theta hat will be a random thing that you calculate from the data. And theta is an unknown parameter in this picture. And we already know some things, which is that, well, if theta, expected value of theta hat is equal to the underlying parameter, is that's if and only if, that's the definition of theta hat being unbiased for theta. So that's the definition. And a more general formula, the bias could be 0 if it's unbiased, or non-zero, it's just expected value of theta hat minus theta. This is a review from a week ago or so. The mean square error of theta hat. Of course, it's all a matter of what you're trying to estimate theta, so that goes without saying when I'm talking about bias and mean squared error. Mean squared error is, of course, the square, you take the random error, square it, and take the expected value. So no big surprise, and as we recall, that's the bias squared plus the variance of theta hat. Now, the best situation is when the bias is 0, but sometimes you can't get 0 bias straight away, so you come up with something else. Okay, so let's talk first about some methods for coming up with point estimators. And we're going to do two main methods. Oh, before I do that, the efficiency. We're only going to define efficiency. Basically, more efficient is better for an estimator. We only want to define it for unbiased because there's a bit of a trade-off between bias and variance. But so, let's say of theta hat with respect to theta tilde. I'm just using two letters for two different estimators. And for this to make sense, I want both to be unbiased for theta. Okay, so two estimators is efficiency of, I guess, theta hat relative to theta tilde is equal to the variance, but I'm going to put the variance of theta tilde on the top and the variance of theta hat on the bottom. Now, because the bias is 0, variance is the same as mean square error. So I could have written mean square error of theta tilde divided by mean square error of theta hat. Why do I say, why is it the theta hat tilde on the top? Only because we want a higher number to be better, more efficient. So a higher number would mean theta tilde has a relatively larger variance and theta hat has a smaller variance. So obviously an estimator, if they're both unbiased, it would be better to have one with less variance, and that's the relative efficiency there. We want as high efficiency as possible. It'll turn out, in general, that there's quite a large class of estimation problems where there is a unique estimator that has the best, a unique unbiased estimator that has the best efficiency. We'll talk a little bit about that later, but the buzzword is sort of unique, minimal variance, and unbiased estimate. So unbiased and minimal variance means highest efficiency. It's the same thing. Okay. But before we do that, we don't really have a lot of general methods for finding point estimates. So, and this could be for one unknown parameter, or it could be for multiple unknown parameters. And both of these methods, with some elaboration, will work in those cases. So first, we're going to talk about method of moments. So we're going to assume this is in the case of an IID sample. So that will be a common thread throughout. So actually, method of maximum likelihood is more general than that. But so for the method of moments, we're going to always assume that x1, x2, xn is a IID and independent identically distributed sample from a, well, it's a parameterized distribution, so a distribution with unknown parameter. So I'll say unknown parameter theta, but you could also do it for multiple parameters that are unknown. Theta 1, theta 2. In principle, you could apply it there. It gets more and more complicated. Then, the method of moments, so to find, I'm just going to do the one parameter case first. Estimator theta hat of theta proceeds as follows. So how does it proceed? Well, we're going to use moments. Now, it's important that I said IID. So we're going to have these raw moments. mu1. Remember, when I did a raw moment, which means a moment around 0, not a centered moment, I used a prime by convention. So that's going to be expected value of x1. The 1 and the 1 are not the same one, because of course mu2 prime is the expected value of the square. So forget about variance for the moment, although if you want to know the second moment, you can of course say that's variance of x1 plus the mean of x1 squared. That would be a good way to find the second moment if you know that. But mu3 prime equals the third moment, dot, dot, dot. Now, you probably won't need all of these. You just go as far as you need. Just pose the equality. Sometimes people might call this an Ansatz, which is a German word meaning just something that you set to be true. There's no particular reason except that we just substitute this into the formula and hope it works. So you just pose the equality mu1 prime. Now, I haven't written the dependence, but mu1 prime will, of course, you calculate these theoretically. I'm not saying that you can calculate this from the sample. You of course, cannot calculate the true moment for a sample. You can only calculate a sample moment from the sample. So these will be calculated theoretically. And why can you do it theoretically? Because you have a distribution that is parametrized. If it was just an arbitrary distribution, you couldn't calculate anything. But parametric distributions have moments in terms of the parameters. Suppose the equality mu1 prime equals, let's just say x bar. That's our normal sample mean. Okay. Now we're not going to use the sample variance to do this. We're just going to continue to use raw moments of the sample, which so mu2 prime equals, I could almost call it x squared bar, but let's not call it that. I'm just going to be totally precise about what it is. 1 over n sum I equals 1 to n of x I squared. So the same as x bar, except you're adding the squares instead of the numbers themselves. And mu3 prime. So on the left-hand side, you'll have functions of theta. You'll have them in terms of theta. And on the right-hand side, you'll have just sample observations. 1 over n sum I equals 1 to n xi cubed. Now, you might not get up to needing mu3 prime. You might not even get up to needing mu2 prime. The principle is, etc. You do as many as you need until you can solve uniquely for theta hat. Okay? So you don't necessarily, you can't solve all infinitely many equations. You just solve the first few. You start from the lowest and go up until you get a unique solution. Now it might be one of two possible solutions or something, but not a whole family of solutions for theta in terms of the sample. Okay. Now let's give these names. I want to call this M2 prime because it would be very tedious to have to keep writing that out. You could call x bar n1 prime if you like. I'm just using m instead of mu to show that it is a sample moment, not a true moment. So sample moment means just take the powers of the sample, add them all up, and divide by m. That's what a sample moment is. So none of those is the sample variance per se. You could get m2 prime in terms of the sample variance and x bar if you did a little bit of algebra. But that's just what they are. So until you get a unique solution for theta in terms of the sample, call this solution theta hat. Now this is a heuristic method, but it does have one important property called consistency, which I'll get to later. I probably won't define consistency right now. But first let's do some examples of this method. So, okay, if multiple parameters theta 1, theta 2, dot, dot, dot. You might need more inputs. Like if you have multiple equations in multiple unknowns, you need more inputs until you solve it. Then continue solving, continue adding, I'll just call these equations start. You always start from the lowest moment and go up until you find a unique solution. And you know, in some cases it may not be technically unique, but unique sensible solution, theta 1 equals theta 1 hat. So all of these at the same time, theta 2 equals theta 2 hat, and so on. Typically you might only have two parameters, for instance mu and sigma. So let's do some examples of this. Now, you might feel, based on this course so far, I'd always start with an IID normal example. That probably would bore you, so let's start with an example that's not IID normal, but one that we've talked about before, which is x1, x2, up to xn, are IID uniform with an unknown parameter, 0 theta. So I'm only treating the right endpoint as unknown and the left endpoint as known. You'll recall when we did this before, one of the ideas was to take the max. We did it in the terms of order statistics. And it turned out the max of x1 up to xn, that was actually a bit less biased for theta. Theta would tend to be a little bit higher than the maximum of all of those. But we could fix that by multiplying by something. So we actually found an unbiased estimator already. Let's see what the method of moments says to do this. Prescribes the following thing. Okay, so it prescribes that we should find, we should put mu1 prime, which is of course expected value of any of the observations, equals x bar. And I would continue if I needed to do more, but what is the expected value of x1? Can anyone tell me what the expected of a uniform 0 to theta? That's right, everyone said theta over 2, that's right. Many ways to do that, but of course it's theta times a uniform 0, 1, which has a mean 1/2. So theta over 2 is the expected value vector. So you see, on the left-hand side I get a function of theta, and on the right-hand side I have something of the sample. So the solution is theta. Now, once I pass to the solution, it's sort of a matter of taste. You could put the theta hat already in this equation, but I'm just putting the theta hat in the equation where I pass to the solution, because to be clear, this is one choice, it's theta. The method of maximum likelihood will actually give a different choice for theta. But theta hat, the choice we're making here, is, and sometimes if you want to make it really clear, you might put a subscript MOM for method of moments. But anyway, theta hat, the solution that I want is 2x bar. So I've just solved this equation for theta. Okay. Now this is quite different from the solution from the estimate that we gave before. Very different. But let's just check its bias. So the expected value of this method of moments estimator is expected value of 2x bar. Now, x bar has the same mean as the individual xi's. You remember that always, whenever there's a mean of the xi's, then x bar has the same mean. So that's 2 times the mean of x1, which is of course theta over 2. So it's theta. So that means the estimator is unbiased. Okay? That frequently happens with the method of moment. You'll find it gives you an unbiased. Not always, but frequently. So it is unbiased, but we sort of want to figure out whether it's any better than the estimator we came up with before. And it's probably a spoiler, but it'll turn out. We did come up with the compared to the other estimator before, which I'm now going to call theta tilde. We had that before. It was you take the maximum guy. Remember, if I do subscript brackets n, that's an order statistic, which means the maximum. And then I have to multiply it by a certain something, n plus 1 over n. That was to make it unbiased. We did this when we were talking about order statistics. Oh, you can't see it. Theta hat is, the light's not great, is it? Okay. We did this before, and I won't rehash the calculation, but the expected value of theta tilde is also equal to theta. If you just did the expected value of the maximum, it turned out to be n over n plus 1. you can redo that using the chapter on order statistics if you like. But so we've got two theta estimators, theta hat and theta tilde. Let's do the relative efficiency. Okay. And before I do it, does anyone have a guess of which of these two estimators is going to be more efficient? Both of them are unbiased, so that's the first step. But you can be more or less efficient. The first estimator was to say, take the average of all of them and double it. Now that is unbiased. And the second one was to take the maximum of all the observations and multiply by n plus 1 over n. Both of those are unbiased for the unknown right endpoint. This right endpoint theta is unknown. Anyone want to hazard a guess which one is more efficient? Which one seems like kind of a smarter idea? This is a vague question, so I'm more than happy for a vague answer. Okay, I've got some observations. I know that they were all uniformly taken from an interval. I just don't know the right endpoint of the interval. I do know that the left endpoint is 0. I want to know what the actual right endpoint of the interval is. Now, one way to guess at that is to take the average and double it. And one way to guess at that is to take the maximum and go a little bit further, multiply by n plus 1 over n. Okay, if we can't guess the variance per se, does either of those methods seem a little bit smarter than the other?
Second one seems.
Yeah, and why?
Because you're using the maximum, so you're kind of getting rid of all the information of ones that are down near 0.
Yeah, that's actually quite a clever way of describing it. So once you know that the maximum is at a certain point, it didn't really matter where the other guys were. Once I know that, okay, or even more basically, if I know that there is an observation bigger than 3, the other observations now have precisely the observations that are less than 3 have no informational value beyond that. Because I know that theta is bigger than 3, and then given that the others were less than 3, they're all uniform, there's no extra information from those. So somehow to care too much about the values below a value that you observe, any values to the left of that is to care about things that don't really matter. That's a vague description, but it turns out to be true. We'll talk a bit more about sufficient statistics later, and that's a way to formalize this. But yeah, so once you know that it's bigger than the maximum, the maximum is sort of the most decisive piece of information, and the other pieces of information are less decisive. By the way, I can give you a more basic reason why this method of moments is a bit of a bad estimate, at least in some cases. There's nothing stopping the mean, or 2 times the mean, being something less than the maximum. If I just have something that's a little bit right skewed, I'd have a whole lot of things towards the left. The mean would be towards the left, and then there would be some points bigger than 2 times the maximum. So it seems like a bad choice to pick a theta hat that could not physically have generated that sample, but that's what the method of moments does. So none of this is to rag on the method of moments too much, other than to say it is a kind of it's just a guess, and it's a natural guess to make, and it does have usually has a consistency property, which I'll talk about in a moment. But consistency, which we'll talk about, is a property about the large n limit. It tells you something about what happens for a huge sample. It doesn't say for a specific size sample that it'll always be sensible. It just says in the limit, over time it will tend to the right answer. But for a specific sample, you could easily have, so let's just, to be concrete about that, you could easily have lots of observations here and all one there. Now, it's kind of unlikely. But if you did have that, then x bar would be here-ish, and 2x bar could easily be there. So you could easily have picked a theta hat, which is not actually bigger than all your observations. So that's another reason. So both of those are good reasons why the second one is a better estimate. We haven't even answered the efficiency question, but we've already given 2 heuristic reasons why it's a better estimate. The first one in particular harks to sufficient statistics, and I'll talk about them in a moment. But for the moment, let's do the relative efficiency so yeah, we would be surprised if theta hat was not better and therefore more efficient than theta tilde, the second one. We'd be surprised if that weren't better. But let's calculate the efficiency. So it is, of course, variance of theta hat divided by variance of theta tilde. Variance of theta hat is, well, it's double the variance of x bar, which is double the variance of the underlying divided by n. Remember, if the underlying has variance sigma squared, then the x bar has variance sigma squared over n. That doesn't rely on normality or anything. It just, variance always goes down by a factor of n when you take the sample mean. So it's of course, there's a factor of 4 from this. 4 times the variance of x1 divided by n. And what is the variance of x1? Well, you may have done the calculation uniform 0, 1 as variance 112, just a calculation. So what does uniform 0 theta have a variance of? Theta squared times 112. It goes as the square. So theta squared divided by 12n. So that is equal to theta squared divided by 3n. Now, of course, what the exact value of that is depends on theta and n. But so will the other ones. Let's do variance of theta tilde. Now, did anyone, don't know whether anyone through the assignment or otherwise, through the assignment or otherwise, whether anyone noticed that when you take order statistics of a uniform, you actually get an interesting distribution, which is beta. Yeah. So, because uniform is beta 1, 1, by the way. Yeah. So, turns out the maximum, any order statistics of betas turn out to be betas. They just kind of put them together and you get a different exponent. So, this guy is actually xn has the distribution which is theta times beta. So just a scaled beta, and the parameters for the beta should be, it's either n1 or 1n. I should be talking over alpha plus beta. And I think it's n comma 1. Someone can double check that for me if they want. That's just a fact about order statistics. You can check it yourself using the CDF or the PDF of an order statistic. So the variance of xn, well, I'd better get a theta squared because of the theta coefficient. And then the variance of a beta, you might remember that it was, gee, what was it? Alpha, on the bottom you had alpha plus beta plus 1. On the top you had alpha times beta, I think. You can double check that if you like. So alpha is n, beta is 1. So it's n times 1 divided by n plus 1, n plus 2. So theta squared n over n plus 1, n plus 2. And then I have to, unfortunately, multiply by this constant. So variance of theta tilde is slightly different. It's, once again, there's theta squared. There's n over n plus 1, n plus 2, and then I have to multiply by n plus 1 over n squared. So n over n plus 1, n plus 2, multiplied by the scaling factor squared, n plus 1 over n squared. Okay. Theta squared times some, rational function which will have n plus 1 divided by n squared brackets n plus 2. Now, okay, that's an exact rational function. We don't have to evaluate it exactly, just observe the behavior for large n. This variance of theta tilde is sort of the order theta squared over n squared, so quite small. So not only is there a constant of improvement, there's more than a constant, there's a whole factor of n that's better here. So if you were to do this relative efficiency, which just on the same page, we have to do a box. The relative efficiency is the ratio of those. So of course, the theta squared cancels out. You would get n plus 1 over n squared n plus 2, and then the 3n would go on top. So 3n plus 1 divided by n plus 2. And whatever you say about that, that tends to 0. It's actually effectively just 3 over n as n tends to infinity. So not only, I guess, is that always greater than 1? Yeah, I think that's always greater than 1. But, yeah. Hang on. I wanted... No. So... What have I done wrong here? I put the 3n on top and the 3n should have been on the bottom. Yeah. So... Yeah. It's that whole thing. It's the reciprocal of that whole thing. And the efficient... This is where, yeah, that thing that I claimed where efficiency you want to be a large number to be more efficient. That's what I fell afoul of. So yeah, it's variance of the lower guy. And why did I say efficiency of theta tilde over theta hat? That's not really what I should have written. I should have written, sorry, that's, okay, I'll fix that. It should have been efficiency of theta tilde with respect to theta hat. So you put the variance of the with respect to on top and you put the variance of the not with respect to on the bottom. It's 3 n minus 1 over n plus 2 inverse. Anyway, it's something that tends to infinity. And it's actually always more than 1. Even for n equals 1, that's going to be 1 times 3 over... oh no, maybe for n equals 1 it's not, but eventually it's larger. Okay, so relative efficiency is in the long run much better for the method of the theta tilde, which will turn out to be the method of maximum likelihood estimation of that. Okay, so let's do that was example 1. Let's do example 2, and this okay, you'll be sick of it, of course. We've got x1, x2 up to xn, but now we're going to treat IID normals. We'll have, this is instructive because it's a good case of having 2 unknown parameters. And let's do it. So we just follow the rules again. You just write down theta, you just write down mu1 prime equals ex1, mu2 prime equals ex1 squared, and so on. So I have to think of, first of all, what are the raw moments of these? Well, of course, the first raw moment is mu. Okay, so mu1 prime, of course, which is mu, but that has to also equal x bar. Okay, and then mu2 prime, you always have to calculate what it is in the specific parametric case based on the parameters. Mu squared plus sigma squared. Remember, that's easy. That's always mean squared plus variance squared for the second raw moment. And we have to set that. By the way, the method of moments consists in imposing these equalities, which are not naturally true. You set mu squared plus sigma squared equal m2 prime. Now, if you want to, I think you can put the hats on at that point already. Somehow I don't like carrying hats around when I'm doing a lot of solving, but let's put hats on them at the end. m2 prime, which is of course 1 over n sum I equals 1 to n of x I squared. Now, for those who want it, you can do everything in terms of x bar and s squared, and to save me that term, what if I had n minus 1 times s squared plus n x bar squared. Remember that the calculation formula for s squared has a minus n x bar squared in it. So if I put that back in, I'll get this nice sum, and then I want to divide that by n. So you can check my algebra, but that's, should anyone dislike this thing, that's another way to write it just in terms of it's the sample variance, conventional sample variance, and the sample mean. Okay, so we've got 2 equations in 2 unknowns. Okay, that so far no big surprise. You normally expect to be able to solve that. There might be issues of plus and minus signs with squares, but for instance, sigma is by convention always taken to be greater than or equal to 0, so we can solve those issues. Usually. In this case, we definitely can. 2 equations in 2 unknowns. Well, this one's pretty easy. The solution, by the time I get to the solution, I'd better give it with hat. So mu hat equals x bar. No big surprise, that's always everyone's point estimate of the mean. Sigma hat, so mu hat squared plus sigma hat squared equals, well, on the one hand, that's x bar squared plus sigma hat squared. On the other hand, it had better be this thing, n minus 1 over n s squared plus n x bar squared. I'm just using this formula rather than that one. You could do it either way. So sigma hat is going to be the square root, I always pick the positive square root for sigma, hat of whatever this is. I mean, at this point, s squared plus n x bar. It's really not working so well today. Let's just get rid of the x bar squared. At this point, I can't really be too bothered to simplify that. I don't think. Can I or can I not? So it turns out that the maximum. One thing to note is that this x bar squared does not cancel out. So, something's a bit strange about this. Well, be that as it may, let me. Alternatively, I'm gonna use this possibly slightly simpler formulation: square root 1 over n sum I equals 1 to n x I squared, which it undoubtedly is. Then subtract the mu squared, which is x bar squared, which is the square root of 1 over n. So 1 to n. So I regret to say I think I did an algebra error in the previous one because it looks too complicated. So yes, here was my algebra error. When I did the s squared and the n minus 1, so I should have done n minus 1 times s squared per se, and then added nx bar squared. Apologies. Yeah. Yes, that was the problem. Yeah, so that's why this. Yeah, so then there is a cancellation. So ultimately equals. So there is an s involved, and then a weird correction factor of square root n minus 1 divided by n. So although I said that the method of moment estimators can sometimes be unbiased, there's no reason that it should be so, and that's especially the case when there's square roots involved or things like that. So, or even without the square roots. Note, sigma squared is not sigma hat squared unbiased for sigma squared, because so in other words, sigma hat squared equals n minus 1 over n times s squared. So s squared is the sample variance that we're all well used to. N minus 1 over n times s squared is actually the sample variance you might define yourself if you weren't otherwise told at the start of a stats course, because that makes sense. You're averaging all the squared deviations. This one is obviously biased to the left. Since s squared is unbiased, this is smaller. This is biased to the left. And the essential reason that it's biased to the left is because by taking out the sample mean tends to move around with the sample. So compared to the true deviations, the deviations from x bar squared are just that little bit small because x bar moves with the sample. And so sigma squared is not unbiased for s squared. And that's just something you have to check the output of both these methods, whether it's method of moments or maximum likelihood. It does not guarantee you an unbiased estimate. Okay, so nevertheless, we were able to solve two equations in two unknowns. Now, before I go on from the method of moments, I want to talk about some more examples, and just to show you some of the things that can go wrong. So let's do an example 3. Sorry, I guess people are probably asking to see the previous one. Let's do an example 3, which will have... There's a reason why I said the vague phrasing that, just keep writing down equations until you get a unique solution, because you may sometimes get sort of dud equations that don't help or don't help as much as you may hope. So let's do an example with one of those dud equations. That would be... now there's a nice name for this distribution called the Laplace distribution. It's probably nicer than is needed, because another name for it is the double exponential distribution. Now it has a rate parameter lambda, double exponential with that parameter lambda. There's a reason all these things are called rate parameters. Now you can probably guess what it is if I just draw it like this. So this guy is just, and that's an exponential decay curve. Now, so far it looks like an exponential random variable. Then the double exponential is, ta-da, it's just a mirror image, or both of them put together. Now, to have both of them put together, I have to have 1/2 the density, because there's twice the area. So the f x of x is 1/2 of what would otherwise be the exponential density, lambda e to the minus lambda x. But of course, I want the left side and the right side, so I'll do absolute value of x. So minus infinity less than x. So that is the density. Another way to say it is that x is, it's kind of a, -1 to the f times y, where f is, let's say, Bernoulli 1/2. So Bernoulli 1/2 is a fair coin, heads or tails, and y is exponential lambda, and f and y are independent. Okay, so that's an equivalent characterization of the Laplace distribution. Now, there's only one parameter here, so you think life should be easy, but can anyone tell me, without even doing calculation, what is the expected value of x? Look at the picture. 0. Anything that's symmetric has expected value 0. There's an asterisk on that statement, which any pedants can probably tell me. Anything that's symmetric that has an expectation has expectation 0. Cauchy distribution, which we talked about once, that tan of a uniform angle, that's a distribution that's symmetric but doesn't have an expectation. So its expectation is not 0, expectation doesn't exist. But so it is fair to say if you have a symmetric distribution, it has expectation either 0 or does not exist. So if this is definitely 0, you've got an exponential tail, that's very easy to check. So the variance of x is of course the same as expected value of x squared. Now there's a little hack or a quick way to do this without calculation. Always try and reuse knowledge if you can. That's why we always recognize certain densities and say, oh yes, this is the density, so I know how to do the integral. This is similar. So let's reuse some work to, if x is just an exponential with a sign that's either plus or minus 1, then what's the expected value of x squared? It's the same as for exponential. The sign has vanished once you square it. So I guess I have to say that's the variance of an exponential plus expected value of y squared. And that shouldn't be too hard because the variance, remember, exponential lambda is just gamma with 1 comma 1 over lambda. So the variance is 1 over lambda squared, and the expected value is 1 over lambda, so square that 1 over lambda. So 2 over lambda squared. So that's the variance of a double exponential or a Laplace distribution. So now if I have x1 up to xn, and I reiterate that the method of moments is adapted to IID samples. It's unlike the maximum likelihood, which can be tweaked. We'll do that later. The method of moments doesn't really have anything sensible to say about something that's not IID. They're IID, Laplace, lambda. Okay? And then by the way, there's a reason for these names rate parameter. You might wonder why I keep going on about rate parameter and scale parameter. They're reciprocals of one another. Because there's two conventions for exponential. Sometimes you call it an exponential b, where b is a scale parameter, then the expected value is b. Sometimes you call it exponential lambda, where lambda is the rate parameter and the expectation is 1 over lambda. So b is 1 over lambda, lambda is 1 over b. Both of those conventions are quite useful because the scale parameter you use in the context of gamma, but the rate parameter has an additive property. We can talk about that later. So anyway, Laplace. So let's just do our method of moments. Expected value of x1, which is 0. That's what mu1 prime is, and I assign that to be x bar. So 0 equals x bar, question mark, question. I mean, that can't be solved, but it's of no use in coming up with a lambda hat value, so you discard. Right? 0 equals x bar hat. So because lambda hat does not occur in this equation, you can't solve for lambda, so discard. So that's why when we say that, you just keep going until you find a solution, this is the kind of thing that can happen. You just get useless equations. Okay, so just keep going. Expected value of x1 squared, which is, mu2 prime. But that we know is 2 over lambda squared. And that should be m2 prime. So we set this guy equals x1. So that guy equals m2 prime. That is 1 over n sum I equals 1 to n of xi squared. I'll just leave it like that, especially given what happened last time. 2 over lambda squared. So lambda hat is going to be found by taking sum of I over I equals 1 to n. Actually, I'd better be 2n divided by sum I equals 1 to n xi squared. But then I better take the square root because there was a so that is the answer. Lambda hat is 2n, square root of 2n over that. I dare say lambda hat would not be unbiased for lambda because square roots tend to mess anything up. Let's just see if we can figure out, because what's the parameter is somewhat a matter of taste. We could also figure out whether lambda hat squared is unbiased for. Now, even lambda hat squared, you've got 1 over a sum of squares. So expected value of 1 over squares are difficult. So I actually don't know for sure, but I would not expect that at all to be unbiased for lambda. There's no particular reason to expect that it would be. Okay, that's the method of moments. So let me give you one defense of the method of moments, having said how rubbish it is in various ways. But it at least tends to give you a number. If there are no other ways to come up with a guess, it gives you a guess. It's the guess that would be right if the sample mean were the true mean. And that's why you come up with it. If the sample mean were the true mean, and if the sample's second moment were the true second moment, that's what you're just substituting those to be equal and you're solving. So there is that sort of logic behind it. And there is one other good feature called consistency. So I have to define this first. And definition, before I can define consistency per se, I need to define convergence in probability. Is to say that if I have, now I'm going to say, to be very suggestive of where this comes from, I'll do theta hat n converges in probability. This is the notation with the brackets p to theta, the limiting value. If there's a number of different ways of saying this. You could say for each epsilon positive, the probability that the distance, so to do distance on the number line, I do absolute value of the difference. So the distance between those two things is bigger than epsilon tends to 0 as n tends to infinity. Convergence in probability. So we say that theta n hat converges in probability to theta if for each epsilon positive. Equivalently, a whole lot of other definitions, but we don't need any others. You're not actually going to have to apply that definition much, because I'm just going to say, so the definition is theta n hat. So this is a sequence of estimators. The definition doesn't actually work for just a single estimator. A sequence of estimators. It's okay in terms of method of moments because that gives a general way to do it for all n. And if you can solve that, then so a sequence of estimators, theta n hat for theta is called consistent. So they're actually a sequence or a family. They're not just a single estimator. If nothing other than this, you expect theta if they converge in probability to theta. You might wonder why there needs to be two definitions rather than just one. This is a very useful concept all over probability, and this is just a particular application of it. So we call them consistent if they converge in probability. And that means, okay, and it's a matter of fact, this is actually the same as converging in distribution to just a constant distribution. There is a constant, like, non-random distribution at each point. That's the same as convergence in distribution. But we tend to phrase it this way. So, fact, method of moment estimators for any number of, could be one or ... if they exist and are unique. So I'm sort of assuming that the method works. There's plenty of cases where it doesn't work. A classic example is where there's no moments. Cauchy distribution has no moments, so method moment's not going to work. But plenty of ways